Okay, so our next speaker is Chiu, and he's going to speak about cosmological constraints from galaxy clusters.
Thank you for having me. My name is Chiu. I'm from National Chengkong University in Taiwan, a small island. And today I'm very grateful and exciting to have this opportunity to share our recent results, cosmology from cluster abundance of the shear-selected, weak lensing shear-selected cluster in the Hyper Suprime-Cam survey. So this was in collaboration with Kaifeng Chen in MIT and also Masamune Oguri in Chiba University in Japan, and also under the collaboration between in the HSC weak lensing groups. So we just submitted 2 papers. You can see the archive number here. It also appear later slides. So if I may, I want to take this opportunity just a few seconds to advertise our university. So we are located at a small island near the mainland China in Taiwan, at NCKU. Our university is one of the top-tier university in Taiwan, and we just moved to the new buildings. We have just quite a few astronomy-related faculties, so we are looking forward to expand our astronomy group. So if you're interested in visiting us or knowing more about our university, feel free to chat with me or send me an email. Okay. So this is the outline of my talk. I first talk about the frontier of the cluster cosmology, observational cosmology, in particular clusters. And I present to you the new route we're using the weak lensing to select a galaxy cluster and to do cosmology. And later I present you the results and the future prospect for the first time. Okay, so I don't think I need to go too much detail about the standard cosmological model because we have heard a lot from the past 3 days. So here I want to just emphasize that all that we know are based on observational evidence. That's what we observe. There's a fact and what we see. So one of the most important observation is, of course, the CMB, cosmic microwave background. So simply put, it's just a single snapshot of the universe at redshift 1100, and it works extremely successful to describe our universe even at late time. And there's an alternative probe to study our universe, which is using the late time structure growth. So in this plot, you can see that the 2 simulation plots on the top shows you the structure formation. As the time evolves, you can see that's a universe with the dark energy, and in the bottom it shows the without dark energy. So it's clear you can see that the structure formation in the universe, simulated universe with dark energy is much slower than the one without dark energy. So this is expected because the presence of dark energy provides anti-pressure, anti-gravity, so it slows down the gravitational collapse. So the structural formation strongly affected by, say, cosmological content inside the universe. So this probe, based on the growth of structure, have already put a very strong constraint on the standard cosmological model and also to test the lambda CDM concordance model. So this is one of the comparison plot that's in terms of the late time and the early time probe in terms of so-called S8 or sigma 8. And we see that the 2 probes from early time and late time do not necessarily agree. And in terms of the S8, we call it S8 tension, which is just a cosmic inhomogeneity at the scale of a megaparsec. So you see on the top panel is the cosmic CMB result from the early time, and all the Pompeo results shown below is a late time probe. They show a roughly statistically slower result, lower value compared to CMB early time. So the extrapolation from the CMB at the redshift 1100 do not agree well with the late time universe at a level about 1 or 2 sigma level, depending how you interpret it. Okay, so here I want to highlight one special probe, which is using a galaxy cluster as a late time probe. So this is also called cluster cosmology. So galaxy clusters are the highest density P of the structure. It traces very well about the cosmological structures. So again, the simulation plot on the top shows the universe with dark energy, on the bottom shows the without dark energy. So the name of, again, the cluster cosmology is try to differentiate these 2 universes and to explain our observations. So in terms of a practical point of view, what we actually do is to compare the so-called halo mass function here This is a number density of a collapsed halos as a function of a halo mass. So you can clearly see that the number density of a cluster, but just based on these observational results, we can strongly rule out the universe without the dark energy here. So you only need, we need a dark energy about 70% to explain what we observe. So the idea is very simple. We just do the cluster counting at different cosmic time, and we can constrain the halo mass function and do cosmology. So this is a state-of-the-art result, just published very recently, early this year, Pocket 24. We just highlight the ray control here. It's just using a few thousand of SPT clusters and to constrain the so-called sigma A versus omega M plane. And in comparison with other modern cluster survey in other different colors. So here you can see that cluster cosmology is really doing very well, very successfully to constrain cosmology. And so far now we have to combine multiple wavelengths to study the gas cluster. You cannot just do this cluster cosmology one single band. And I also want to remind you that current sample size of the cluster cosmology is just a few thousand systems. That translates to the sky coverage roughly just a 1 or 2% sky coverage. So you can see that's a great potential once we have a full sky survey. Okay, this is another comparison. Again, SPT cluster result in rate in comparison with other non-cluster cosmology result. So here, I just want to say that the abundance of a cluster still remains the most powerful, one of the most powerful constraining probe in terms of a growth-based methods. Here you can compare with the other BAO or Planck is in blue, and that's just green one is the cosmic shear 3x2 correlation function from DAS. So you can see that cluster, just based on cluster abundance, is a very powerful method. And here I want to also talk about the Eero-theta final equatorial depth survey, EFAS. This is the Eero-theta selected cluster cosmology that we just published last year. So this is also the first Eero-theta based cosmology. So the total number is about 500 clusters, spanning a redshift between 0.1 to 1.2. And we confirm each system, so the sample is very pure. Contamination rate is less than 6%. And we also have a weak lensing coverage to calibrate, to measure the mass for individual system, about a majority of them. So we can really model the weak lensing, the mass of a cluster, model the weak lensing profile. And we also understand the selection, so we can model the so-called X-ray count rate distribution of the cluster. And then we can calibrate this cluster mass as a function of redshift and do the cluster cosmology. And individual mass uncertainty is about 20%. So this gives you the result, which is the flat standard CDN constraint. EFAS cluster are in blue. And you can see on the left-hand side shows the standard SA versus omega M plane. Here I also want to highlight the Planck constraint with the neutrino free. That's in purple. So you can see just a 500 cluster, you can have a slightly worse result than all sky CMB. And also in turn, if you open up the W, you can put a constraint on equation of a state of dark energy with uncertainty about 0.5. Again, so it's all based on just 500 cluster. So again, it's a very promising and interesting probe. Okay, now just also very recently, just this year, we have a first Eero-theta all-sky map from the Eero-theta telescope. And from this half-sky sample, we can derive also, again, the cluster cosmology. The results shown by this orange contour here. That's published in Geodiny 24. So there's a lot of different contour just showing you a different cluster cosmology result. But so far, just based on the Eero-theta all-sky survey, the original contour is the tightest constraint on cosmology we obtained so far. I want to just draw your attention on this blue circle here, just a Planck CMB result. So you can see that the cluster abundance is really providing competitive constraint and complementary constraint to the CMB. Okay, so I have talked about the conventional cluster cosmology. So far, the typical strategy is to detect galaxy cluster based on the Baryoni tracer. It's an X-ray or tracing the galaxy distributions. And once you have a cluster sample and you follow up in optical survey, you confirm the system, measure the redshift and the richness, and further to clean out the sample. The most important thing is to measure the cluster mass. Otherwise, you cannot do the mass function calibration. So in this place, we need a scaling relation to get the to connect the mass proxy, for example, X-ray luminosity to underlying halo mass. And in the end, you can compare your halo mass function of prediction and do the cosmology. So however, this strategy has a very serious issue, which is the baryonic selected cluster are subject to the selection effect, meaning that you are not directly looking at the total cluster mass. Instead, you're looking at some X-ray luminosity or some baryonic tracers, which have a complex relation connecting to the underlying halo mass. So here we propose a new route, which is using a weak lensing weak lensing selection to select galaxy cluster. Then in this way, we only rely on the gravity to select the clusters and no assumption about the baryonic physics. So this gives you a weak lensing shear-selected cluster sample. So we just construct a mass map and directly identify the mass peaks as a cluster sample and to do our cosmology. So this is a purely gravity-based sample without any baryonic assumption, so free of any baryonic bias. And currently, only the Hyper Suprime-Cam Subaru survey can achieve this task because the requirement to do this cluster cosmology is very high. You need a very deep and excellent image. So just in case you are not familiar with the Hyper Suprime-Cam survey, this is a 1100 wide field and the deep survey. It's the deepest optical survey in the achieved area. With the source density roughly more than 20 galaxies per arc square. And the uniqueness of this survey is that it's very deep and very wide, and image quality is excellent. This is the most powerful weak lensing machine, especially at the high redshift. They allow us to do a cluster cosmology, a shear-selected cluster cosmology. So here, this I present you series 2 paper that we have carried out to do a weak lensing shear-selected cluster using the latest HSC year 3 500 square degree weak lensing data. Paper 1, we describe the sample and also a selection. And paper 2 present you a cosmological constraint. Here, I'm going to show you the result. So this is a weak lensing mass map. You are seeing here is the 500 square degree disputing 6 different fields. You can see that the color coded is the signal to noise ratio of the mass map. And you can directly identify the peaks as a galaxy cluster. So here we have a 129 shear-selected cluster with a signal to noise ratio larger than 4.7 over the 500 square degree. This is the largest shear-selected cluster sample ever built. And out of 129, about 122 clusters are real system because it's very pure, so there's no fake system here. So this is the only equation I will show in this talk. So what we do is very simple. We just have a theoretical predicted halo mass function, and we have observed signal to noise ratio function, as shown by example here. And we need to compare these two by a relation, so-called scaling relation. P of a given observed signal to noise ratio given the mass and redshift. And here we can decompose this equation into 3 components. The first describe the intrinsic scatter for given halo mass. The halo profile looks slightly different. The second component is the measurement uncertainty because the observations. And third component is the sample completeness. So the profile are described by 2 very simple parameters. One is kappa, it's just normalization of a profile, and also the compactness, just the extendedness of a halo mass profile. So we quantify this selection using directly on the mass map. Here is the work carried out by Kai-Feng Chen in MIT. So we just we inject a fake cluster in the observed mass map with a wide range of a mass profile. For this case, this is the same cluster with a mass 5 times 10 to the 14, very massive, and at a ratio 0.35. We inject a different location of the mass map. This is a before and after injection. And we test our detection pipeline and quantify our measurement uncertainty. And in this way, we can derive the so-called, for example, the miscentering of a cluster of a detection, also same cluster over the 500 injection, what is the distribution of observed signal to noise ratio for given cluster mass and redshift. So we repeat this test a lot of time for different mass and ratio of a cluster, and we can construct this so-called completeness map. You can see that on the left. This figure shows you the completeness map as a function of the halo profile normalization, kappa, and the theta s. You can see 3 crosses. For each crosses here, since we inject a lot of a cluster, so we can derive the distribution of observed signal to noise ratio for this pixel. So each pixel here, we have this distribution. So in this case, we can directly quantify our scaling relation, selection, and measurement uncertainty directly on the mass map. So this is we also take into account the photo Z bias. We have two approach, but I'm running out of time. So I just show you the results. That is we have the photo Z bias. As a worst cases, we have a 2 sigma bias at ratio 1.2, and we take that into account. So these are all the parameter I have. This have a selection function and also mass frequency, mass bias, for photo Z bias, etc. And I'll just show you the result. So this is the observed signal to noise ratio function of the data of 129 cluster, and the bronze line is the best fit to the model. You can see that this is an excellent description of the data. And we also don't see the internal tension in the data because we don't see the deviation at the different fields. So there's no internal tension in the data. So this is a parameter posteriors. We take into account a lot of Newton parameters, and one of the most important parameters here is the sigma A and omega m, but this is series degeneracy. We cannot constrain that. Instead, what we can constrain is the parameter space perpendicular to this direction. We call it S8 height here. So this is the only interesting parameter we can constrain in this work. So this is a result. Again, on the left-hand side, show you the sigma A versus omega m plane. The blue contour is our result. And this is in comparison with the other cluster cosmology result, SPT result in green. And on the right-hand side, I show you a standard S8 versus omega m in comparison with, for example, Planck and 3x2 correlation function and cosmic shear from HSE. You can see that agreement is 1 sigma, although we have a degeneracy in a very serious degeneracy in omega m. So this is another, what we can constrain is the perpendicular direction in this parameter space. So we can derive this S8 hat, which is the omega n to the power 2.25. That's shown in this plot. You can see that the Planck result is in here. We have results here. We can summarize our result here. This is our result. You can see that in our result, we do not see a strong S8 tension between the CMB data and the cluster, also along with other cluster results. And interestingly, I want to point out that if you're using the same data to do cosmic shear, they also prefer a higher value, no sigma A tension, no S8 tension. But if you include the GG lensing to get the 3x2 correlation function, it prefers slightly lower, but not significantly, just a 1 or 2 sigma level. Okay, we performed a series of robotics tests. We tuned a lot of different parameters and done it blindly and unblind, and this result is, we think it's robust. Just my final slide is the future prospect. So currently, our look lensing community is playing quite conservatively because we don't have a capability to calibrate fan source and the cluster inner core. So here, we just only use in this world, we only use the source away from the cluster center, and also we throw out a lot of low Z source. So we only use half of the source sample we have. We deliver roughly 10 galaxies per army square. So in the future, in the end, so as a result, we only have a low resolution mass map, so we can only resolve a high mass system at a low redshift. So in the future, if we want to push the data, we need to increase the resolution. So we need to have more source. So we need to understand the galaxy distribution as a function of a halo mass, redshift, magnitude, and radius. And I think calibrating this weak lensing shear-selected cluster using the X-ray sample will be the key to the future. Okay, this is my take-home messaging, and here I'll just say we do not see a statistically significant S8 tension between the cluster and the CMB result. And we have then just using the 100 cluster, we can get the 4 to 5% constraint on S8. I stop here. Happy to take questions. Thank you.
Questions?
Thanks for the very interesting talk. So you mentioned that HSC is the only survey that can do this. I'm trying to understand why that is, because kids is not that much shallower and the resolution is not so much worse after all.
Right,
It covers, I think, larger scale area than what you have now. So what would be the limiting factor that even going to kids is already not?
It's an excellent question. Thank you for asking. Sorry, I did not explain very well. So kids, of course, there's a larger area, but it's the source density is the key. So kids has something 5 or 6 galaxy per arc square. That means you need to resolve the mass map. You cannot resolve the mass map very properly. So your resolution of a mass map is worse. So you cannot see the cluster unless you are looking for a very, very massive cluster. So of course you can carry out the same experiments and you have a mass map from DES or from KISS. But the key factor is that resolution of a lost mass map is very low. So you can only resolve maybe 10 or 20 cluster. It's much, much less than the HSC.
And you used a weak lensing shear selection method for galaxy cluster. Did you try to compare the accuracy of this method with respect to optical matching algorithm or color selection based algorithms for the detection of galaxy clusters?
Yes, excellent question. Yeah, we did, and we did quite a lot in a paper because there will be a boring from the talk, so I didn't mention that. We not only compared to the optical cluster, we also compared to X-ray cluster, SZ cluster. So we're quite confident that we also look at every image we have. So we're quite confident that our sample purity is more than 99%. So that is, yeah, we do compare that. Thank you.
I just want a question about the consistency between the cluster results. It kind of, like, to me, it looks like they're not that consistent with each other. Can you comment on that? And then, the kind of related question is, what is the systematic that you're most worried about?
Yes, thank you. That's an excellent question. So I think you're mentioning this here. So let's just for this S8 hat, and talking about the consistency, we say that the consistency between the Planck is very good. It's less than 1 sigma. So only discrepancy we see is with the 3x2. That's also not very
within the clustering.
Yeah, just within the
just clustering, no others probe, just clustering.
Just clustering. No, we didn't compare just.
We had a plot before that compared the different clustering results, and it kind of showed that they weren't really consistent with each other.
So clustering means 3x2 correlation function.
I mean cluster counts.
So Planck is here, and all the clusters are this Planck, and the very recent E rho theta all sky is give you the 2 sigma. So I think based on their paper, they don't claim this as a statistical evidence for.
No, I don't mean with Planck, within the cluster.
Within the cluster, we see.
It's like one of the results looks like it's 10 sigma away.
Oh, that's right. We know the reason because from DES, they have a weak lensing calibration issue for a low Z system. It's one of the selection bias. So we know the cause for this contour. So this contour is basically the selection modeling is not fully correct. So it gives you the bias. And I will answer your second question is the most important factor here is the weak lensing mass calibration. You need to get the mass calibration accuracy down to 1% level. Otherwise, you will bias systematically. So this is the most important thing. You need to do the weak lensing right. I hope that answers your question.
Okay, thank you everyone for the questions. It's not the time to continue.